Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on January 30th, 2026, just about a week ago. It introduces a novel architecture that decouples feed-forward networks from the self-attention mechanism, transforming them into interpretable memory units and reducing versus RAM requirements by roughly 2/3. The paper is titled LLM, Plug-and-Play Interpretable Feed-Forward Memory for Transformers. And as we'll see later, the results for efficient deployment on resource-constrained devices are really impressive. To understand the structural shift, Figure 1 compares the standard architecture with this new design. The top panel illustrates a conventional dense large language model. Notice how the feed-forward module receives data that has already been processed by the self-attention mechanism, meaning its input depends heavily on the changing context. The bottom panel shows memory LLM. Here, the feed-forward block is decoupled. It bypasses the self-attention loop entirely and connects directly to the static input embedding, labeled X0. This forces the layer to act as a consistent memory lookup, independent of the residual stream. Equation 2.6 defines the update rule that makes this possible. It shows that the next layer state, XL+1, combines the previous state and the attention output, which both still depend on the evolving context XL. However, the final term changes everything. The feed-forward network is a function of X0. Because X0 comes directly from the static tokenizer IDs, this mathematically guarantees that memory retrieval remains completely independent of the residual stream. So having established that the input is static, Figure 2 details the actual mechanism, called the Token Key Value Framework. At the top, raw text is tokenized and mapped to static embeddings to form query vectors. In the middle, the up projection matrix acts as a set of key cells. The query vector calculates memory coefficients here, which are then reweighted by a learned gate. Finally, the bottom section shows the retrieval step, where these coefficients combine with the down projection matrix, treated as value cells, to produce the final output. Since these memory keys rely on static inputs, we can map out exactly which tokens activate which parts of the network. Figure 5 visualizes this relationship using a TSNE plot of the key contribution vectors. The results show clear semantic clustering. For example, the zoomed-in region on the top right reveals that punctuation marks and code symbols group tightly together. Similarly, the inset at the bottom right contains almost exclusively personal names, like Walter and Antonio. This demonstrates that the model spontaneously organizes its memory by semantic and lexical properties. Moving beyond the semantic clusters, Table 1 tests the functional role of these memory modules by slowly turning them off. The authors introduce a scaling factor, alpha, which gradually reduces the feed-forward network's contribution from 1.0 down to 0.5. On the left side, we see recall-dominated tasks like Wikitext2 and Lambda. Notice how performance here collapses dramatically. Specifically, Wikitext2 perplexity degrades by over 120% when alpha hits 0.5. By contrast, the logical reasoning tasks on the right, such as Hella Swag and PIQA, are much more robust. This suggests that while the feed-forward layers are critical for retrieving facts, the model's reasoning capabilities largely live elsewhere. Well, recognizing that the pure memory approach can struggle with complex reasoning, Figure 8 presents a hybrid solution called Flex-MemoryLLM. On the left, Panel A displays the basic memory LLM block, where all feed-forward parameters, denoted as 8h², are dedicated to the static memory. Panel B, on the right, shows the Flex variant. Here, the authors carve out a portion of those parameters to create a new FFN compute module, shown in pink. This module processes the dynamic output from self-attention, while the remaining capacity stays in the static memory, effectively balancing active reasoning with efficient retrieval. Alright, Figure 11 shows why this design might be a better alternative to traditional model pruning. Here, the authors compare Memory LLM and Flex-MemoryLLM against standard compression techniques like SparseGPT and Wanda. The graphs plot perplexity on the vertical axis against the number of active parameters on the horizontal axis. As we move to the right, the models become more efficient, but notice how the gray pruning curves shoot upward, indicating a massive spike in error. In contrast, the colored shapes for the new architecture stay low and stable, hugging the red dashed baseline even at extreme compression levels. Wrapping up, 2 takeaways stand out. Decoupling the feed-forward networks transforms them into transparent, interpretable memory banks, and offloading these static lookups drastically reduces versus RAM requirements. This points toward a future where we can run powerful, explainable models directly on consumer devices. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.